In the last video, we defined linear independence, and now we will look at some examples. More precisely, we will be characterizing sets of vectors that are linearly independent in R2. In this process, we will also observe some general phenomenon and they will also be discussed in this video. Now notice that if you take only one vector v, then irrespective of what that vector is, as long as the vector is not the zero vector, it is always going to be linearly independent. On the other hand, if you take two vectors, say v1 and v2, then they will be linearly independent if and only if v1 is not equal to alpha times v2 for any alpha in R. Once again, we will be assuming that the vectors v1 and v2 are not equal to 0. Zero vector, as soon as we have one zero vector in the collection cannot be linearly independent. Therefore, we will always assume from now on that the vectors that we are considering are all non-zero. Let us now look at some particular examples. If we look at a vector, say v1 is equal to 1, 0, then if you want v2 to be linearly independent with 1, 0, then it cannot be of the form x, 0. Any vector that is not of the form x, 0 will be linearly independent. One example, for instance, would be 0, 1, which clearly is not of the form x, 0. But there are plenty of other examples. For instance, we could have taken v2 to be 1, 1. Or we could have taken v2 to be 2, 3 or 3, 5 or any of these numbers. There are so many different options that would make v2 linearly independent with v1. Now the same thing we could have done with some other choice of v1. For instance, we could have taken our first vector itself to be equal to 2, 3. Then how can we choose another vector such that the two are linearly independent? Of course, as we already saw that 1, 0 is one such vector. What other vector can we choose? Once again, it will be linearly independent if it is not a scalar multiple of 2, 3. For instance, we can take the vector v2 to be 3, 2. Notice that there does not exist any alpha such that 2 times alpha, 3 times alpha is equal to 3, 2. So these two vectors v1 and v2 are linearly independent with each other. Similarly, we can construct as many examples as you wish of two vectors that are linearly independent. Next, we ask a question. Can we find three vectors v1, v2, v3 such that the three are linearly independent? Now, first we observe that there are two possibilities for us. Either v2 is equal to alpha times v1 or v2 is not equal to alpha times v1. If v2 is equal to alpha times v1, then the three vectors v1, v2, v3 cannot be linearly independent. This is because the sum alpha v1 plus minus 1 into v2 plus 0 times v3 is equal to 0. However, alpha, minus 1, 0 is not equal to 0, 0, 0. And thus, this collection is not linearly independent if v2 is equal to alpha times v1. Therefore, without loss of generality, we can assume that v2 is not equal to alpha times v1. Now we saw in our discussion in 3.1 that as soon as v2 is not equal to alpha times v1, the span of v1, v2 is equal to the entire R2. This means that if you take any vector v3, I can write this as alpha times v1 plus beta times V2. This once again implies that the three vectors are not linearly independent. Why? Because we can write a sum alpha times V1 plus beta times V2 plus minus 1 times V3, which is equal to 0. But clearly alpha, beta, comma minus 1 is not equal to 0, comma 0, comma 0. And thus the three vectors cannot be linearly independent. We have thus shown that irrespective of what the three vectors v1, v2, v3 are, they cannot be linearly independent. Now notice that if we have a collection of vectors that are linearly independent, then any subcollection is also going to be linearly independent. Let us try to see a proof of this fact. We will prove this by using a proof by contradiction. To do this, we have to first assume the contrary. What is the contrary in this case? The contrary is that the vectors vi1, vi2, etc. up to vik are not linearly independent. In other words, there exist constants ai1, ai2, etc. up to aik such that ai1, ai2, etc. up to aik is not equal to the 0 vector. And ai1 vi1 plus etc. up to aik vik is equal to 0. So we assume that such a collection of constants ai1, ai2, etc. up to aik exists. Once we have these constants, define ai to be equal to 0 if I does not belong to the set I1, I2, etc. up to ik. Then notice that a1, a2, etc. up to an is not equal to 0, 0, etc. up to 0. However, a1 v1 plus a2 v2 plus etc. up to an vn is equal to ai1 vi1 plus etc. up to aik vik. And we assume that this is equal to 0, which implies that we have constants a1 to an such that a1 v1 plus a2 v2 plus etc. up to an vn is equal to 0. Moreover, these constants are not all equal to 0, which implies that v1, v2, etc. up to vn are not linearly independent. This is a contradiction. Why? Because it is given that v1, v2, etc. up to vn are linearly independent. Therefore, our assumption that vi1, vi2, etc. up to vik are not linearly independent has to be wrong. And thus, we have proved that vi1, vi2, etc. up to vik are linearly independent. This completes the proof. Now, consider four vectors v1, v2, etc. up to v4 in the vector space R2. Now, notice that if these four vectors were linearly independent, then any collection of three vectors from this will also be linearly independent. But we saw that a collection of three vectors cannot be linearly independent in R2. Therefore, v1, v2, etc. up to v4 are not linearly independent. In general, v1 to vn is linearly independent implies that n is less than or equal to 2. Once again, notice that this 2 and this 2 are related to each other. In other words, in R2, the maximal linearly independent set has cardinality 2. Moreover, as we saw that the subset of a linearly independent set is linearly independent, it makes sense to talk about maximally linearly independent sets. What are they? We say a set V1 to Vn is maximally linearly independent if V1 to Vn are linearly independent, but V1 to Vn, comma V is not linearly independent for any vector V in the vector space. We will now prove a theorem that completely characterizes maximally linearly independent sets in R2. A set V1 to Vn in R2 is maximally linearly independent if and only if n is equal to 2. That means there are only two vectors V1 and V2, and those two vectors are linearly independent. Let us now try to see a proof of this. First, we will consider the case where n is equal to 1. That means the set contains a single vector. Let's call that vector V. Now, if V is equal to 0, then it is not linearly independent and hence is not maximally linearly independent. Therefore, we can assume that V is not equal to 0. If V is not equal to 0, then as V belongs to R2, we can write V as, say, x comma y. If x is equal to 0, then this implies that V is equal to 0 comma y. And notice that 0 comma y and y comma 0 are linearly independent. Therefore, if x is equal to 0, the set 0 comma y is not maximally linearly independent. On the other hand, if y is equal to 0, once again we can write V as x comma 0, and notice that x comma 0 and 0 comma x are linearly independent. Therefore, if x or y is 0, then x comma y cannot be maximally linearly independent. Therefore, we may assume that x is not equal to 0 and y is also not equal to 0. In this case, we claim that x comma y and x comma minus y are linearly independent. How do we see this? To see this, we consider a and b to be two constants such that a into x comma y plus b into x comma minus y is the 0 vector, which is given by 0 comma 0. But a into x comma y plus b into x comma minus y is equal to a plus b into x comma a minus b into y. As x and y are non-zero, this implies that a plus b is equal to 0 and a minus b is equal to 0. A minus b equal to 0 implies that a is equal to b. Therefore, a plus b is 2a, which is equal to 0, which implies that a is equal to 0. But as b and a are equal, this implies that b is also equal to 0. Therefore, both a and b are equal to 0. Thus, we have proved that x comma y and x comma minus y are indeed linearly independent. Now consider the case n is equal to 2. That means we have two vectors v1 comma v2. If suppose v1 comma v2 are not linearly independent, then obviously the set v1 comma v2 is not maximally linearly independent. Why? Because a maximally linearly independent set has to be linearly independent to begin with. Therefore, we can assume that v1 comma v2 are linearly independent. Further, notice that we had already shown that if you take any three vectors in R2, they cannot be linearly independent. Therefore, v1, v2, v will not be linearly independent for any v in R2. This implies that v1, v2 is maximally linearly independent. Thus, we have shown that if you have two vectors and they are linearly independent, then the set containing these two vectors has to be maximally linearly independent. And finally, we had also seen that if n is greater than or equal to 3, then the set v1 to vn cannot be linearly independent. And as it is not linearly independent, it cannot be maximally linearly independent. Thus, a set v1 to vn is maximally linearly independent only in the case where n is equal to 2. Moreover, even when n is equal to 2, it will be maximally linearly independent only when they are linearly independent. Thus, we have proved the theorem. We will end this video by showing that any maximally linearly independent set has to span the vector space. To show this, let v1 to vn be a maximally linearly independent set. Thus, if v is any vector in the vector space v, then v1 to vn, comma v cannot be linearly independent. That means there exists constants a1 to an and a such that a1 v1 plus etc. up to an vn plus av is equal to 0. Moreover, a1 to an comma a is not equal to 0 comma etc. up to 0. Further, notice that a is not equal to 0. Because if a was equal to 0, then we have a1 v1 plus a2 v2 plus etc. up to an vn is equal to 0, where a1 to an are not all 0, which will imply that v1 to vn are not linearly independent. But we assumed that the set v1 to vn is maximally linearly independent, which means that they are linearly independent. Therefore, a cannot be equal to 0. But as a is not equal to 0, we can rewrite v to be equal to minus of a1 by a times v1 plus etc. up to minus of an by a times vn. That means v can be expressed in terms of v1 to vn. In other words, v lies in the span of v1 to vn. But notice that v was an arbitrary vector in the vector space v. That means every vector in the vector space v belongs to the span of the vectors v1 to vn. And thus we have proved that these vectors span the vector space v.